100. I'm Professor Curtis, your instructor for this course, and this is the lecture video for Chapter 17, Change of State. Let's get started. So, physicists are really fond of talking about four phases of matter: solid, liquids, gases, and plasma. Well, that's the physicist. I'm an engineer, not a physicist, and that really just because they use that word phase, and that really just throws me off because we engineers have a very different perspective on that word phase. So the reason why we just get so bent out of shape with it is because we use the phase to talk about different crystal structures in a material. So remember earlier we talked about crystal structure and how it's really important to know the crystal structure because that ties into the mechanical properties of your material and the thermal properties of your material. Well, in order to distinguish between different materials that have different, crystal structures, we use this word phase. And a good example is in a common engineering material that we all know about. It's called steel. So steel has many different crystal structures in it, and there's different combinations that you see there. And what you see there on the right is what's known as a phase diagram. So if you look down here, one of the things you notice really quickly is that you don't need a lot of carbon in order to make steel. And that's amazing. I mean, you just add 1 or 2% carbon and you've got a material that's way more strong, way more malleable, way more flexible, way more durable than what iron is without the carbon added to it. So just a little bit of carbon can go a long way. But these different areas that we see here on the phase diagram are showing you different phases of the iron depending upon how much carbon you have mixed in with your iron and then what temperature your material is at. So here we're at some elevated temperatures here, but notice this very top line that you see here, this is what's called the liquidus line, and so above this line the steel is going to be in a liquid form, a molten form like you see here in the ladle. Well, if you go below this liquidus line, then it starts to solidify. So these regions here, just below the liquidus line, are what we look at. We're looking at molten steel, where some of it's liquid and some of it is solid. Then these next sets of lines here are what we call solidus lines, because below those lines, the material is completely solidified. It's now solid. It's in the solid state. And so notice how we've got different crystal structures here, different areas here. Each of these different areas are mixes of different crystal structures. So, for example, we've got austenite, which is in the gamma phase, and then we've got ferrite, which is an alpha phase. And the main distinguishing between these two different types is the crystal structure. Okay, ferrite has a body-centered cubic crystal structure. Austenite, face-centered cubic crystal structure. So if you look at austenite and ferrite, they both got the same amount of iron. They both got the same amount of carbon. They both got, they're both solid materials. So how do we distinguish between them? What word do we use to distinguish between the different situations we've got there? And that's where the word phase comes in. We use the word phase to distinguish between those different portions where everything's solid, but it's a different crystal structure. And so to distinguish between solids, liquids, and gases, engineers like to use the word state. And since I'm an engineer, that's what I'm going to use in my lecture presentation. So I'm going to talk about states of matter. Now notice I only talk about solids, liquids, and gases. What happened to plasma? Well, I'm not like the physicists that separate that out. Most engineers that I know don't distinguish plasma as a separate state of matter. We just look at that and say it's just an ionized form of gas. And so we consider that to be in the gas state. The fact that it's ionized doesn't change the actual state that it's in. So, a lot of us engineers part ways with the physicists when we talk about that. I bring this up because the author of your textbook is a physicist. So he's going to look at, all of his stuff differently than I am. And I'm sharing with you the perspective so that if you see the difference, you know the reason behind that difference. Now, we talked earlier in previous lectures about the different state of matter and the differences between them. So we've got the solid state, the liquid state, the gas state, and we know that all of these states of matter have atoms and molecules where those atoms and molecules are vibrating in place, but the way in which they move relative to their neighbors is different. So with solids, everything's pretty much tethered in place, so everyone's in their little house. And then with the liquid state, yeah, you're going out and visiting the neighbors, but you're still kind of in the same neighborhood. And then with gases, you're going all over the place. Who knows where you're off to? You see changes in density with solids, liquids, and gases. So with solids, there's no change in the density. With liquids, you can change the density by changing the the temperature. And with gases, you can change the density by changing the temperature or the pressure or both. So I want to bring this up because we're going to be examining in this lecture for this chapter more of the reasons why we see these different behaviors in the different states of matter. And what we're really going to examine to look at the differences between the different states of matter is looking at changes from one state to another. Whenever you're changing the state of a substance, it always requires some energy transfer. Energy is either going into your system or it's coming out of your system. And the direction of that energy transfer, whether it's coming in or out, is going to depend on the direction of the state change you're looking to have. So gases have much more internal energy than solids. So if you want to change your state to be closer to the gas state, then that's going to give energy off. Okay, because gases have, if you're moving closer to the solid state, you're going to give energy out. Gases have more energy than solids. So in order to go closer to the solid state, you got to get rid of that excess energy. You got to go to a lower energy state, get rid of your extra energy. So it's going to give energy out. If you go the other way, you want to get closer to the gas state, that's going to take energy because now you got to bring in energy that you didn't have. You got to take energy into your system. So looking at the spectrum from solids to gases, if we're moving in a direction that moves us closer to the gas state, that state change is going to take energy. So we have to put energy into the system in order to make that state change happen. To go the other way, okay, if we want to go closer to the solid state, and that means we've got to give energy out. You get energy out of the system, okay? Notice this is from the perspective of the surroundings. Okay, so you've got the system that's experiencing the state change, and then surroundings is everything outside the system. So from the perspective of the surroundings, if you've got a state change that takes energy, where's that energy coming from? Well, it's coming from the surroundings. This comes from the surroundings into the system. You're putting energy into the system, taking energy out of the surroundings. Likewise, if you go back the other way and say, I want to get closer to the solid state, well, to bring your system closer to the solid state, you've got to get rid of that excess energy. So energy has to go out of the system. It goes into the surroundings. And that energy out of the system means it's giving energy to the surroundings. There are specific names for each of the different types of state changes that we could experience. But the direction of that energy transfer makes sense when you consider the differences in relative movement of the molecules for the different states of matter. So gases having more energy, the molecules and the atoms are going to be moving around much faster than you are if you're in the solid state. And so, again, from the perspective of the surroundings, if you're moving closer to that gas state, you got to put energy into the system. And that's why in the table there, you see energy in is considered to be a negative energy direction because it's from the perspective of the surroundings. The energy is lost from the surroundings to go into the system. So because it's a loss in the surroundings, that makes it negative. If you flip that around and go the other way, See, now you've got energy coming out of the system into the surroundings. So now the surroundings are gaining energy, and that's why that energy direction is considered to be positive. So you've got all the different names here for your different state changes. I highly recommend that you commit these to memory because you probably will see this again in homework assignments and on your test. So make sure you understand what the names are for each of these different state changes, and more importantly, what direction is the energy going in for each of these different state changes. So for molecules of a substance to move relative to each other, it takes energy. Okay? And again, from the perspective of the surroundings, is energy going into the system or is energy going out of the system? And knowing which way the energy is going is important because that's going to help us to understand how the energy is moving about. How are we proceeding to thermal equilibrium? Here's an excellent little video. Does a great job of showing phase changes relative to the movement of molecules within a material. So let's check this out.
When a solid gets warm enough, it melts. To explain what's happening, imagine you can see how the particles in a solid are arranged. They're in a fixed framework, vibrating but not straying far from their main position. When energy is supplied, the particles vibrate more violently and become free to move. The solid changes into a liquid. Melting involves a transfer of energy. This can be illustrated by putting an ice cube in a sealed container, leaving another one empty. The air on the left is at 25.5 degrees Celsius. As the ice melts, it takes energy from the surroundings. The temperature of the air in the right-hand container has fallen by about 3 degrees. Energy is also needed to change a liquid to a gas. So, what's happening to the particles this time? In a liquid, the particles are free to move around. Heating causes them to move around more quickly. Those which have enough energy escape from the liquid, forming a gas. This is evaporation. Ether evaporates at room temperature. It's taking energy from the surroundings and disappears in less than 5 minutes. It's possible to see how different liquids take heat from their surroundings using thermometers wrapped in string. They all start off at room temperature. The string absorbs the liquids. Number 1 on the left is a control. Number 2 is dipped into water, 3 into ethanol and 4 into ether. As soon as the string leaves the liquid, evaporation gets underway. The temperature of thermometers 3 and 4 quickly begins to drop. As the liquids evaporate, they're taking energy from the string, the air, and even the bulb of the thermometer. So, which has taken most energy from its surroundings? Liquid 2, 3, or 4? Gases can also be changed into liquids. For this to happen, they need to be cooled. Liquid nitrogen is extremely cold. Immerse a balloon full of air in it and see what happens. The balloon shrinks and becomes brittle. Inside, you can see a liquid. It's liquid air. This time, the balloon is filled with carbon dioxide gas. Immerse it in liquid nitrogen and it cools rapidly. What's inside the balloon this time? If a gas gets cold enough, it changes into a solid. This is solid carbon dioxide. See how it changes back to a gas at room temperature.
All right, so really good job, like I said, of demonstrating phase changes there. And notice how the energy for all those systems to change it into, it comes from the surroundings. And so, that's where the direction of the heat transfer becomes really important, because it lets us know, which direction are we changing for our state change. So in the video, the temperature of the air surrounding melting air dropped a little bit, and that's because to go from solid to liquid, you got to put energy in, and the energy, like I said, is coming from the surroundings. So if you take energy out of the surrounding air, there's less energy for those molecules to move around, and that means less average kinetic energy of the particles, so the temperature goes down. So temperature is related to the state of matter that you're in, and also to the changes of state that you're going to experience as you go from one to another. So on your worksheet, you're going to see various names and types of changes of state, and there's some information missing. So for some, the name's missing. For others, the type of state change is missing. So if the type is given, supply the missing name. If the name is given, go ahead and supply the missing type. And then there's a column there on the right for you to identify the direction of energy transfer. So which way does the energy go during this state change? Is energy going into the system, or is it coming out of the system? So go ahead, stop the video, take a moment to fill that in. Try not to look back at what we went through with that earlier table, where you can find all the answers there, obviously. So try not to look back at there, because you want to get in the habit of learning this stuff and have it fixed, and having an experience in which you trip up a little bit and then learn the information is actually going to cement it in your head better than if you just copy the answers from something you're looking at. You're not going to learn much with that. So go ahead, stop the video, try this activity out, and then come back and we'll see how you did with it. All right, let's look at what you did. So first item there, sublimation. This is a state change from a solid to a gas. And when you're getting closer to that gas state, the energy direction is going to be negative. That's energy into the system. Next, going from a gas to a liquid, that's called condensation. And I guess moving from a gas to a liquid, you're moving away from the gas towards the solid state. Get closer to the solid state, that's going to be energy out, which is a positive energy direction. Next, we've got going from a solid to a liquid. This is called melting. And because we're moving away from the solid towards the gas, that means we've got energy going into the system, and that's a negative energy direction. Next, we've got evaporation, boiling, or vaporization. They're all three names for the same thing, going from a liquid to a gas. And because we're going closer to the gas state, this represents energy in, which is a negative energy direction. Cooling, freezing, solidification, that's going from a liquid to a solid, and that means we're going to take energy out of the system, which is the positive energy direction. And finally, we have deposition, which is a gas going directly to a solid state, and here we've got energy coming out of the system. It's a positive energy direction because going out of the system means you're going into the surroundings. That's a gain for the surroundings. So again, you want to be able to commit some of this stuff to memory because it'll help you understand the direction of the energy as it's going during a change of state. Now, I said temperature was related very much with the change of state, and the way it's related is that it marks boundaries between the different states of matter. So at a set pressure, okay, there's going to be different temperatures that mark the boundaries between solid, liquid, and gas. And the boiling point is what we call the boundary between the liquid and the gas states. The melting point, some people call this the freezing point, marks the boundary between solid and liquid states. Now, these boundary temperatures are going to change with pressure. So unless specified, you're really going to be assuming we've got standard pressure, which is 1 atmosphere or 101.3 kilopascal. This is the standard that's typically used by convention. Sometimes you get, questions about, state changes at different pressures, but for most of what we're going to look at, we're just looking at standard pressure, which is 1 atmosphere. Now, here's an important point. Substance must assume a boundary temperature to change state. So in other words, you've got to have that boundary temperature in order to cross over the boundary. Now, when you reach the boundary temperature, the entire substance will remain at that temperature until all of the substance has changed state. It's a very important point. So while you're in that state change, the temperature of your substance will remain constant at that boundary temperature. Only until all the substance is transformed into the new state do you begin to see a rise in temperature. So far, what we've discussed is the direction of energy transfer during a state change. Now we're going to talk about how much energy gets transferred. And to do this, we need to introduce a concept called latent heat. Latent heat is the amount of energy that you need to change state. Now, of course, because there are different boundary temperatures for changes of state, there's going to be different latent heats. There's a separate latent heat associated with each boundary temperature. So the latent heat of fusion is the amount of energy needed to change between the solid and the liquid states. Okay, now the direction of the energy transfer is determined by which direction you're going. So if you're going from a solid to a liquid, okay, that's taking energy out of the surroundings and putting it into the system. If it's going from liquid to solid, it's going the other way. But the amount of energy that's crossing over the boundary between the two states, that's going to be the same amount of energy because it's set amount to change the state of a material from one state to the next. Then the latent heat of vaporization is what we associate with the energy needed to change between the liquid and the gas states. So latent heat of fusion is what we use to transform between solid and liquid states. Latent heat of vaporization is what we use to transform between liquid and gas states. Let's look at an example involving water to illustrate what we've just learned. So here we've got a graph that's showing the heat versus temperature as we do a state change from solid to gas. We've got 1 gram of water at standard pressure, and we're going to start at the origin of our graph there, negative 50 degrees centigrade. We put heat in to our system, the 1 gram of water, and we raise its temperature to 0 degrees Celsius. So now we're here at this point on the graph. We're ready. We're at that boundary temperature between the solid and the liquid states, and now we're going to transform our substance from the solid state to the liquid state. So to do that, we have to add in the latent heat of fusion. So we take this latent heat of fusion and we're going to add in 335 joules. This is the latent heat of fusion, 335 joules per gram. We've got 1 gram, so we need to add in 335 joules. So notice that brings us to this point here on the graph. And the temperature remained constant during that state change. That's why the line is horizontal. The temperature is not increasing while you have that state change. So now all of our ice has been converted to liquid water, and we're at 0 degrees, so now we need to get up to 175. So now we need to add more heat energy in order to raise the temperature. And to do that, we're going to add in 418 joules to bring us to the next boundary. So where does the 418 come from? Well, that comes from that relationship that we saw previously between heat and temperature. Q equals Cm delta T. So we take the specific heat of water times the 1 gram, which is the mass, times the change in temperature, which is 100 degrees. They get from the one boundary to the next, and that gives us the 418 joules. That brings us to this point on the graph. Now we're ready for the next state change, going from liquid to gas. And that requires the heat of vaporization. Notice the heat of vaporization is a lot bigger than the heat of fusion. This is pretty typical for most materials. It takes a lot more energy to go between liquid and gas states than it does to go between solid and liquid states. So we take in that latent heat of vaporization, the 2,255 joules, and that brings us over here, and then we can continue adding. Now we're in the gas state. We continue adding heat energy into our system to raise the temperature up to 175. But again, notice that when you're in the state change, the temperature is constant. That's why at those points, the line there on the graph is horizontal. The temperature is not changing. And that's because temperature doesn't change when you're doing a state change until all of the substance is changed. Here's a final video. Provides a really good wrap-up of most of what we discussed so far regarding changes of state. It's a little spotty in a couple places, so just bear with it. But yeah, this video is a pretty good overview of what we looked at so far.
There are 3 states of matter: solid, liquid, and gas. Any substance can go from one state of matter to another state of matter by changing temperature or pressure or both. These are physical changes, not chemical changes. Remember, all of these particles are moving. They have kinetic energy, which is the energy of movement. Solids have the least kinetic energy, liquids have more, and gases have the most. So to change the phase, you can alter the pressure or temperature to get the desired state of matter. To go from a solid to a liquid, you add energy to melt it. But to go from a liquid to a solid, you'd want to remove kinetic energy by decreasing the temperature, and that's freezing. Similarly, a gas can become a liquid by lowering its temperature and condensing. When a liquid's temperature increases enough, it can vaporize to become a gas. Let's take a moment here to talk about vaporization so we can clarify a few things. Under the umbrella of the term vaporization are 2 ways to get liquids into gases. The first type is evaporation, which occurs at the surface of a liquid that is not boiling. This is like when you spill a drop or 2 of water on the table and leave it there. After a while, the water is gone, but you didn't have a blowtorch on it to heat it up. The surface particles have enough energy to escape the liquid and become vapor until eventually the whole drop of water becomes vapor. Boiling is the rapid vaporization of liquid at the boiling point. In this case, you would either add heat or lower the external pressure on a liquid to get to the boiling point very quickly. Both methods make vapor, but boiling is much faster. Now back to the phase changes. Now solids can also skip the liquid phase and go directly to gas under the right conditions, usually low pressure or temperature. It's called sublimation. This is how we freeze-dry food and why dry ice, which is solid carbon dioxide, makes great spooky fog at Halloween. Gas can also go directly to solid in a process called deposition, which is also sometimes called desublimation. The way I've organized the states of matter makes for a pretty chart, but doesn't do the greatest job of showing how adding energy makes a difference, so I'm going to adjust them slightly. Now these are in the order of increasing energy. Just remember that sublimation and deposition skip the liquid phase. Now I could also be more specific when I write increasing energy. I could say increasing kinetic energy. Kinetic energy is the energy of movement. Particles are always moving. Particles of a solid move less than particles of a liquid, and particles of a gas move the fastest. But not every particle is moving at the same speed. Some are moving a little slower, and some a little faster. But the average kinetic energy of a group of particles is temperature. This bell curve shows the kinetic energy for particles in a sample of matter, and the average energy of the particles is temperature, which we measure in Celsius. The temperature at which a solid becomes a liquid is the melting point. Using a chart like this, you can figure out what temperature you need to get a solid, liquid, or gas phase of the substance you're using. For example, if you're performing a lab that requires liquid oxygen, you need a temperature between the melting point and boiling point, which is where the liquids exist. So the oxygen will have to be cooled to at least negative 183 degrees Celsius, but not as cold as negative 218 degrees Celsius. A container of liquid nitrogen could help us get to those temperatures. Now suppose you want to use bromine in its vapor form. You would need to heat it past its boiling point. Gas or vapor phases are all above the boiling point temperature. Bromine is a liquid at room temperature, so it only needs a little more heat to get it to vaporize. Now let's say you found some mercury and wanted to make it solid. You would have to cool it down to at least negative 39 degrees Celsius, its melting point, to get solid mercury. At room temperature, which is around 23 degrees Celsius, everything that boils below 23 degrees is a gas, so that's neon, oxygen, and chlorine for this chart. Anything where 23 degrees is between the melting and boiling point is a liquid at room temperature, so that's ethanol, mercury, bromine, and water. And lastly, anything that has a melting point higher than room temperature is a solid at room temperature, like sulfur, gold, and copper. Thanks for watching this episode of Teacher's Pet. Don't forget to like and subscribe and follow me on Twitter at SciencePet.
Yeah, so like I said, it's a little spotty in a couple places, but overall it's got a really good overview of what we're looking at here with changes of state. And that brings us to the end of this lecture. I hope you found it helpful. Thanks for watching, and we will see you in the next video.